Well, so far we've invented enough programming to do some very complicated things, and you've surely learned a lot about programming at this point. You've learned almost all the most important tricks that usually don't get taught to people until they have a lot of experience. For example, data-directed programming is a major trick. And yesterday you also saw an interpreted language. We did this all in a computer language at this point where there was no assignment statement. And presumably, for those of you who've seen your BASIC or Pascal or whatever, that's usually considered the most important thing. Well, today we're going to do something horrible. We're going to add an assignment statement. And since we can do all these wonderful things without it, why should we add it? An important thing to understand is that today we're going to, first of all, have a rule which is going to always be obeyed, which is the only reason we ever add a feature to our language is because there's a good reason. And the good reason is going to boil down to the ability, you now get an ability to break a problem into pieces that are different sets of pieces than you could have broken it down without that, giving you another means of decomposition. However, let's just start. Let me begin by reviewing the kind of language that we have now. We've been writing what's called functional programs, and functional programs are a kind of encoding of mathematical truths. For example, when we look at the factorial procedure that you see on the slide here, it's basically two clauses. If n is 1, the result is 1. Otherwise, n times factorial n minus 1. That's factorial of n. Well, that is factorial of n. And written down in some other obscure notation that you might have learned in calculus classes, mathematical logic, what you see there is if n equals 1, the result for n factorial is 1. Otherwise, greater than 1, n factorial is n times n minus 1 factorial. True statements. That's the kind of language we've been using. And whenever we have true statements of that sort, there's a kind of a way of understanding how they work, which is that such processes can be evolved by substitution. And so we see on the second slide here that the way we understand the execution implied by those statements arranged in that order is that you do successive substitutions of arguments for formal parameters in the body of a procedure. These all say, this is basically a sequence of equalities. Factorial of 4 is 4 times factorial of 3. That is 4 times 3 times factorial of 2, and so on. We're always preserving truth. Now, even though we're talking about true statements, there might be more than one organization of these true statements to describe the computation of a particular function, the computation of the value of a particular function. So, for example, looking at the next one here, here's a way of looking at the sum. If you look at the sum of n and m, okay, and we did this one by a recursive process. It's the increment of the sum of the decrement of n and m. Okay. And of course, there is some piece of mathematical logic here that describes that. It's the increment of the sum of the decrement of n and m. Just like that. So there's nothing particularly magic about that. And of course, if we can also look at an iterative process for a program that evolves an iterative process for the same function, these are two things that compute the same answer. And we have equivalent mathematical truths that are arranged there. And just the way you arrange those truths determine the particular process, or the way you choose and arrange them determines the process that's evolved. So we have the flexibility of talking about both the function to be computed and the method by which it's computed. So it's not clear we'd need more. However, today I'm going to do this awful thing. I'm going to introduce this assignment operation. Now, what is this? Well, first of all, there's going to be another kind of statement, if you will, in our programming language called set. And set, things that do things like assignment, I'm going to put exclamation points after. We'll talk about what that means in a second. The exclamation point, again, like question mark, is an arbitrary thing we attach to the symbol, which is the name, has no significance to the system. The only significance is to me and you, to alert you that this is an assignment of some sort. But we're going to set a variable to a value. Okay. And what that's going to mean is that there is a time at which something happens. Here's a time. If I have time going this way, this is a time axis. Time progresses by walking down the page. Then an assignment is the first thing we have that produces the difference between a before and an after. All of the other programs that we've written that have no assignments in them, the order in which they were evaluated didn't matter. But assignment is special. It produces a moment in time. So there is a moment before the set occurs, and after, such that after this moment in time, the variable has the value independent of what value it had before. Set changes the value of the variable. Until this moment, we had nothing that changed. So, for example, one of the things we could think of is that the procedures we write for something like factorial are in fact pretty much identical to the function factorial. Factorial of 4, if I write FACT4, independent of what context it's in, and independent of how many times I write it, I always get the same answer. It's always 24. It's a unique map from the argument to the answer. And all the programs we've written so far are like that. However, once I have assignment, that isn't true. So, for example, if I were to define count to be 1, and then I'm going to define also a procedure, a simple procedure called demo, which takes an argument x and does the following operations. It first sets x to x plus 1. My gosh, this looks just like Fortran, right? In a funny syntax. And then add to x count. Oh, I just made a mistake. I want to say set count to 1 plus count, which is this thing defined here. And set plus x count. Then I can try this procedure. Let's run it. So suppose I get a prompt and I say demo of 3. Well, what happens here? The first thing that happens is count is currently 1. Currently, there's a time. I'm talking about time. X gets 3. At this moment, I say, oh yes, count is incremented, so count is 2. 2 plus 3 is 5. So the answer I get out is 5. Then I say demo of, say, 3 again. Okay, and what do I get? Well, now count is 2. It's not 1 anymore because I've incremented it. But now I go through this process. 3 goes into x. Count becomes 1 plus count, so that's 3 now. The sum of those two is 6, so the answer is 6. And what we see is the same expression leads to 2 different answers depending upon time. So demo is not a function. Does not compute a mathematical function. In fact, you can also see why now, of course, This is the first place where the substitution model isn't going to work. This kills the substitution model dead. You know, with quotation, there were some little problems that a philosopher might notice, okay, with the substitutions, because you have to worry about what deductions you can make when you substitute into quotes, if you're allowed to do that at all. But here the substitution model is dead. Can't do anything at all. Because supposing I wanted to use a substitution model to consider substituting for count. Okay? Well, by gosh, if I substitute for here and here, okay, they're different ones. It's not the same count anymore. I get the wrong answer. A substitution model is a static phenomenon. It describes things that are true, and not things that change. Here we have truths that change. Okay, well, before I give you any understanding of this is very bad. Now we've lost our model of computation. And pretty soon I'm going to have to build you a new model of computation. But let's play with this just now in an informal sense. Of course, what you already see is that when I have something like assignment, the model that we're going to need is different from the model that we had before, in that the variables, those symbols like count or x, are no longer going to refer to the values they have, but rather to some sort of place where the value is stored. We're going to have to think that way for a while. It's going to be a very bad thing and cause a lot of trouble. Okay, so as I said, the very fact that we're inventing this bad thing means that there had better be a good reason for it. Otherwise, it's just a waste of time and a lot of effort. Let's just look at some of it, though, just to play. Supposing we write down the functional version, functional meaning in the old style, okay, of factorial by an iterative process. Factorial of n we're going to iterate of m and I, which says if I is greater than n, then the result is m. Otherwise, it's the result of iterating the product of I and m. So m is going to be the product that I'm accumulating. M is the product. Okay? And the count I'm going to increase by 1. Plus iter else condefine. I'm going to start this up. And these days you should have no trouble reading something like this. What I have here is a product being accumulated and a counter. Okay, I start them up both at 1. I'm going to buzz the counter up. I goes to I plus 1 every time around. But that's only where I'm putting a time on the process. Each of this is just to have truths, true rules. Okay. And m is going to get new values of I and m, I times m each time around. And eventually I is going to be bigger than n, in which case the answer is going to be m. Now I'm speaking to you, use time in this. That's just because I know how the computer works. But I didn't have to. This could be a purely mathematical description at this point, because substitution will work for this. But let's write down a similar sort of program using the same algorithm, but with assignments. So this is called a functional version. I want to write down an imperative version. Factorial of n. I'm going to create my two variables. Let I initialize itself to 1 and m be initialized to 1, similar. We'll create a loop. Which says cond greater than I n. If I is greater than n, we're done, and the result is m, the product I'm accumulating. Otherwise, I'm going to write down three things to do. I'm going to set m to the product of I and m, set I to the sum of I and 1, and go around the loop again. Looks very familiar to you Fortran programmers. Else con define. Funny syntax, though. Start the loop up. Okay, and that's the program. Now this program, how do we think about it? Well, let's just say what we're seeing here. There are two local variables, I and m, that have been initialized to 1. Okay. Every time I round the loop, I test to see if I is greater than n, which is the input argument. And if so, the result is the product being accumulated in m. However, if it's not the end of the loop, if I'm not done, then what I'm going to do is change the product to be the result of multiplying I times the current product, which is sort of what we were doing here. Except here I wasn't changing. I was making another copy. Because the substitution model says you copy the body of the procedure with the argument substituted for the formal parameters. Here I'm not worrying about copying. Here I've changed the value of m. I also then change the value of I to I plus 1 and go buzzing around. Seems like it's essentially the same program. But there are some ways of making errors here that didn't exist until today. For example, if I were to do the horrible thing of not being careful in writing my program and interchange those two assignments, the program wouldn't compute the same function. I get a timing error because there's a dependency that m depends upon having the last value of I. If I try and change I first, then I've got the wrong value of I when I multiply by m. It's a bug that wasn't available until this moment, until we introduced something that had time in it. So as I said, first we need a new model of computation, and second we have to have a damn good reason for doing this kind of ugly thing. Are there any questions? Speak loudly, David.
Okay. I'm confused about, we've introduced set now, but we had let before and define before. I'm confused about the difference between the three. Wouldn't define work in the same situation as set if you introduced it?
No, define is intended for setting something once the first time, for making it. Okay? In other words, you have never seen me write on a blackboard, okay, two defines in a row whose intention was to change the old value of some variable to a new one.
And is that by convention or?
No, it's intention. Okay? The answer is that, for example, internal to a procedure, two defines in a row are illegal. Two defines in a row of the same variable. Okay? Executing the same define twice. Whether or not a system catches that error is a different question. But I legislate to you that define happens once on anything. Now, indeed, in interactive debugging, we intend that you interacting with your computer will redefine things. And so there's a special exception made for interactive debugging. But define is intended to mean set up something, okay, which will be forever that value after that point. Okay? It's as if all the defines were done at the beginning. In fact, the only legal place to put a define in scheme internal to a procedure is just at the beginning of a lambda expression, okay, which is the beginning of the body of a procedure.
Now,
okay. Now let of course does nothing like either of that. I mean, if you look at what's happening with a let, this happens again exactly once. It sets up a context where I and m have values 1 and 1. That context exists throughout this scope, this region of the program. However, you don't think of that let as creating as setting I again. It doesn't change it. I never changes because of the let. I gets created because of the let. In fact, the let is a very simple idea. Let does nothing more. Let a variable 1 to have value 1. Let me write this down a little bit more neatly. That's right. var 1 have the value of expression E1, and variable 2 have the value of the expression E2. In an expression E3 is the same thing as a procedure of var1 and var2 being formal parameters, and E3 being the body, where var1 is bound to the value of E1 and var2 gets the value of E2. So this is in fact a perfectly understandable thing from a substitution point of view. This is really the same expression written in two different ways. In fact, the way the actual system works is this gets translated into this before anything happens.
Okay, I'm still unclear as then what makes the difference between a let and a define. They could
a define is a syntactic sugar whereby essentially a bunch of variables be created by lets and then set up once. Okay, time for the first break, I think. Thank you. Let me get this. 7. How long was that? Well, let's see. I now have to rebuild the model of computation so you understand how some such mechanical mechanism could work that can do what we've just talked about. I've just recently destroyed your substitution model. Unfortunately, this model is significantly more complicated than the substitution model. It's called the environment model. And I'm going to have to introduce some terminology, which is very good terminology for you to know anyway. It's about names, and we're going to give names to the kinds of names things have and the ways names are used. Okay, so this is a meta description, if you will. Anyway, there's a pile of unfortunate terminology here, but we're going to need this to understand what's called the environment model. And we're about to do a little bit of boring dog work here. Let's look at the first transparency. And we see a description of a word called bound. Okay. And we're going to say that a variable v is bound in an expression E if the meaning of E is unchanged by the uniform replacement of a variable w not occurring in E for every occurrence of v in E. Now, that's a long sentence. Okay, so I think I'm going to have to say a little bit about that before we even fool around at all here. Bound variables we're talking about here. And you've seen lots of them. You may not know it, you've seen lots of them, although I suppose in your logic you saw logical variables like for every x there exists a y such that p is true of x and y from your calculus class. Okay. this variable x and this variable y are bound because the meaning of this expression does not depend upon the particular letters I use to describe x and y. If I were to change w for x, so it said for every w there exists a y such that p is true of w and y, it would be the same sentence. That's what it means. Or another case of this that you've seen is integral, say, from 0 to 1 of dx over 1 plus x squared. Okay? Well, that's something you see all the time, and this x is a bound variable. If I change that to a t, the expression is still the same thing. This is a quarter of the arctan of 1 or something like that. That's, yeah, it's arctan of 1. So bound variables are actually fairly common for those of you who've played a bit with mathematics. Well, let's go into the programming world. Instead of the quantifier being something like for every, or there exists, or integral, a quantifier is a symbol that binds a variable. Okay, we're going to use the quantifier lambda as being the essential thing that binds variables. And so we have some nice examples here, like that procedure of one argument y, which does the following thing. It calls the procedure of one argument x, which multiplies x by y and applies that to 3. That procedure has the property that there are two bound variables in it, x and y. This quantifier lambda here binds this y, and this quantifier lambda binds that x. Because if I were to take an arbitrary symbol that does not occur in this expression, like w, and replace all y's with w's in this expression, the expression is still the same procedure. And this is an important idea. The reason why we have such things like that is a kind of modularity. If two people are writing programs, it should be, and they work together, it shouldn't matter what names they use internal to their own little machines that they're building. Okay? And so what I'm really telling you there is that, for example, this is equivalent to that procedure of one argument y, which uses that procedure of one argument z, which multiplies z by y, because nobody cares what I used in here. Okay? It's a nice example. On the other hand, I have some variables that are not bound. An example. That procedure of one argument x, which multiplies x by y. In this case, y is not bound. Supposing y had the value 3, okay, and z had the value 4, okay, then this procedure would be the thing that multiplies its argument by 3. If I were to replace every instance of y with z, I would have a different procedure which multiplies every argument is given by 4. Okay, and in fact, we have a name for such a variable here. We say that a variable v is free in an expression e if the meaning of the expression e is changed by the uniform replacement of a variable w not occurring in e for every occurrence of v in e. Okay, so that's why this variable over here, y, is a free variable. And so free variable in this expression. And other examples of that is that procedure of one argument y, which is just what we had before, which uses that procedure of one argument x that multiplies x by y. Use that on 3. This procedure has a free variable in it, which is asterisk. See, because if that has the normal meaning of multiplication, then if I were to replace uniformly all asterisks with pluses, then the meaning of this expression would change. That's what you mean by a free variable. So far you've learned some logician words which describe the way names are used. Now we have to do a little bit more playing around here. A little bit more. I want to tell you about the regions over which variables are defined. You see, we've been very informal about this up till now. And of course, many of you have probably understood very clearly, or most of you, that the x that's being declared here is defined only in here. Okay? This x is defined only in here, and this y is defined only in here. Well, we have a name for such an idea. It's called a scope. And let me give you another piece of terminology. It's a long story. If x is a bound variable in E, then there is a lambda expression where it is bound. So the only way you could get a bound variable ultimately is by a lambda expression. Now you may worry, there's defined quite this, an exception to this. And it turns out we can always arrange things so you don't need any defines. And we'll see that in a while. It's a very magical thing. Okay, so define really can go away. Okay, the really only thing that makes names is lambda. That's its job. And what's so amazing about a lot of things is that you can compute with only lambda. But in any case, okay, a lambda expression has a place where it declares a variable. We call that the formal parameter list. And we say, or the bound variable list. We say that the lambda expression binds, so it's a verb, binds the variables declared in its bound variable list. And in addition, those parts of the expression where the variable is defined, which was declared by some declaration, is called the scope of that variable. So these are scopes. This is the scope of y. And this is the scope of x. That sort of thing. Okay. Well, now we have enough terminology to begin to understand how to make a new model for computation. Because the key thing going on here is that we've destroyed the substitution model, and we now have to have a model that represents the names as referring to places. Because if we're going to change something, then we have to have a place where it's stored. You see, if a name only refers to a value, and if I tried to change the name's meaning, well, that's not clear. There's nothing that is the place that name referred to. Or how am I really saying it? There's nothing shared among all of the instances of that name. And what we really mean by a name is we fanned something out. We've given something a name, and you have it, because I've given you a reference to it, and I've given you a reference to it. And we'll see a lot about that. So let me tell you about environments. I need the overhead projection machine. Thank you. Okay, so here is a bunch of environment structures. An environment is a way of doing substitutions virtually. It represents a place where something is stored, which is the substitutions that you haven't done. It's a place where everything accumulates, where the names of the variables are associated with the values they have, such that when you want to say what does this name mean, you look it up in an environment. So an environment is a function, or a table, or something like that. But it's a structured sort of table. It's made out of things called frames. Frames are pieces of environment, and they're chained together in some nice ways by what's called parent links or something like that. So here we have an environment structure consisting of three environments basically, A, B, and C. D is also an environment, but it's the same one. They share. And that's the essence of assignment. If I change a variable, a value of a variable that lives here, like that one, it should be visible from all places that you're looking at it from. Say this one, x. If I change that x to 4, it's visible from other places. But I'm not going to worry about that right now. We're going to talk a lot about that in a little while. What do we have here? Well, these are called frames. Here's a frame, here's a frame, and here's a frame. A is an environment which consists of the table labeled, which is frame 2, followed by the table labeled frame 1. And in this environment, in say this environment, frame 2, x and y are bound. They have values. In frame 1. In frame 2, z is bound, and x is bound, and y is bound. But the value of x that we see looking from this point of view is this x. Its x is 7, rather than this one, which is 3. We say that this x shadows this x. Okay. From environment 3, from frame 3, from environment B, which refers to frame 3, we have variables m and y bound, and also x. Okay. This y shadows this one. So the value, looking from this point of view, of y is 2. The value for looking from this point of view of m is 1. And the value looking from this point of view of x is 3. So there we have a very simple environment structure made out of frames. These correspond to the applications of procedures. And we'll see that in a second. So now I have to make you some other nice little structure that we build. On the next slide, we see an object which I'm going to draw procedures. This is a procedure. A procedure is made out of 2 parts. It's sort of like a cons. Okay. However, it's the 2 parts. Okay. The first part refers to some code, something that can be executed, a set of instructions, if you will. You can think of it that way. And the second part is an environment. The procedure is the whole thing. And we're going to have to use this to capture the values of the free variables that occur in the procedure. If a variable occurs in the procedure, it's either bound in that procedure or free. If it's bound, then the value will somehow be easy to find. Okay? But I will talk, it'll be in some easy environment to get at. If it's free, we're going to have something that goes with the procedure that says where it'll go look for its value. And the reasons why are not obvious yet, but will be soon. So here is a procedure object. It's a composite object consisting of a piece of code and a environment structure. Now I will tell you the new rules, the complete new rules for evaluation. Okay. The first rule, there's only 2 of them. These correspond to the substitution model rules. And the first one has to do with how do you apply a procedure to its arguments. Okay. And a procedure object is applied to a set of arguments by constructing a new frame. That frame will contain the mapping of the formal parameters to the actual parameters of the arguments that were supplied in the call. As you know, when we make up a call to a procedure like lambda x times xy, and we call that with the argument 3, then we're going to need some mapping of x to 3. It's the same thing as later substituting, if you will, the 3 for the x in the old model. So I'm going to build a frame which contains x equals 3 as the information in that frame. Now, the body of the procedure will then have to be evaluated, which is this. And it will be evaluated in an environment which is the in the environment which is constructed by adjoining the new frame that we just made to the environment which was part of the procedure that we applied. So I'm going to make a little example of that here. Supposing I have some environment, here's a frame which represents it, and some procedure, which I'm going to draw with circles here because it's easier than little triangles. Sorry. Those are rhombuses. Rhomboidal little pieces of fruit jelly or something. So here's a procedure which takes this environment. And the procedure has a piece of code, which is a lambda expression, which binds x and y, and then executes an expression e. And this is the procedure. We'll call it P. I wish to apply that procedure to 3 and 4. So I want to do P of 3 and 4. Well, what I'm going to do, of course, is make a new frame. I build a frame which contains x equals 3 and y equals 4. And I'm going to connect that frame to this frame over here. Okay. And then this environment, which I will call B, is the environment in which I will evaluate the body of E. Now, E may contain references to x and y and other things. X and y will have values right here. Other things will have their values here. How do we get this frame? That we do by the construction of procedures, which is the other rule. And I think that's the next slide. Rule 2. When a lambda expression is evaluated relative to a particular environment, see, the way I get a procedure is by evaluating a lambda expression. Here's a lambda expression. By evaluating it, I get a procedure which I can apply to 3. Now, this lambda expression is evaluated in an environment where y is defined. And I want the body of this, which contains a free version of y. Y is free in here. It's bound over the whole thing, but it's free over here. I want that y to be this one. I evaluate this body of this procedure in the environment where y was created. That's this kind of thing, because that was done by an application. Now, if I ever want to look up the value of y, I have to know where it is. Therefore, this procedure when it was created, the creation of the procedure, which is the result of evaluating that lambda expression, had better capture a pointer or remember the frame in which y was bound. Okay, so that's what this rule is telling us. So, for example, if I happen to be evaluating a lambda expression in E, lambda of, say, x and y, let's call it g in E, evaluating that, well, all that means is I now construct a procedure object. E is some environment. E is something which has a pointer to it. I construct a procedure object that points off to that environment, where the code of that is the lambda expression or whatever that translates into. And this is the procedure. So this produces for me, this object here, this environment pointer, captures the place where this lambda expression was evaluated, where the definition was used, to make a procedure, to make the procedure. So it picks up the environment from the place where that procedure was defined, stores it in the procedure itself, and then when the procedure is used, the environment where it was defined is extended with the new frame. So this gives us a locus for putting where a variable has a value. And for example, if there are lots of guys pointing at that environment, then they share that place. And we'll see more of that shortly. Well, now you have a new model for understanding the execution of programs. I suppose I'll take questions now, and then we'll go on and use that for something.
Is it right to say then the environment is that linked chain of frames?
That's right.
Starting with working all the way back?
Yes. The environment is a sequence of frames linked together, and the way I like to think about it is the pointer to the first one. Because it's, once you've got that, you've got them all. Anybody else?
Is it possible to evaluate a procedure or to define a procedure in two different environments such that it will behave differently and have pointers to both?
Oh, yes.
The same?
Oh, the same procedure is not going to have two different environments. The same code, the same lambda expression, can be evaluated in two environments producing two different procedures. Each procedure...
Their definition has the same name, their operation.
The definition is written with the same characters. Right. I can evaluate that set of characters, whatever, or that list structure that defines, that is the textual representation. Okay? I can evaluate that in two different environments producing two different procedures. Each of those procedures has its own local sets of variables, and we'll see that right now. Okay? Anybody else? Okay, thank you. Let's take a break. Well, now I've done this terrible thing to you. I've introduced a very complicated thing, assignment, which destroys most of the interesting mathematical properties of our programs. Okay? Why should I have done this? What possible good could this do? It's clearly not a nice thing, so I better have a good excuse. Well, let's do a little bit of playing, first of all, with some very interesting programs that have assignment. To understand something special about them that makes them somewhat valuable. Start with a very simple program, which I'm going to call make counter. I'm going to define make counter to be a procedure of one argument n, which returns as its value a procedure of no arguments. There's a procedure that produces a procedure, which sets n to the increment of n, and returns that value of n. Okay. Now we're going to investigate the behavior of this. It's a sort of an interesting thing. And in order to investigate the behavior, I have to make an environment model, because we can't understand this any other way. So let's just do that. We start out with some sort of, let's say there's a global environment that the machine is born with. Global, we'll call it. And it's going to have in it a bunch of initial things. We all know what it's got. It's got things in it like say, plus, and times, and quotient, and difference, and car, and etc. Lots of things. I don't know what they are. Some various squiggles that are the things the machine is born with. And by doing the definition here, what I plan to do, well, what am I doing? I'm doing this relative to the global environment. So here's my environment pointer. In order to do that, I have to evaluate this lambda expression. That means I make a procedure object. So I'm going to make a procedure object here. And the procedure object has as the place it's defined the global environment. The procedure object contains some code that represents a procedure of one argument n, which returns a procedure of no arguments, which does something. And the define is a way of changing this environment so that I now add to it make counter. A special rule for the special thing define. But what that is it gives me that pointer to that procedure. So now the global environment contains make counter as well. Now, we're going to do some operations. I'm going to use this to make some counters. We'll see what a counter is. So let's define C1 to be a counter beginning at 0. Of 0. Well, we know how to do this now, according to the model. I have to evaluate the expression make counter in the global environment. Make counter of 0. Well, I look up make counter and see that it's a procedure. Okay? I'm going to have to apply that procedure. The way I apply the procedure is by constructing a frame. Right? So I construct a frame which has a value for n in it, which is 0. And the parent environment is the one which is the environment of definition of make counter. Okay? So I've made an environment by applying make counter to 0. Now I have to evaluate the body of make counter, which is this lambda expression, in that environment. Well, evaluating this body is a lambda expression. Evaluating a lambda expression means make a procedure object. So I'm going to make a procedure object. And that procedure object has the environment it was defined in being that, where n was defined to be 0. And it has some code, which is the procedure of no arguments, which does something, that sets something, and returns n. And this thing is going to be the object, which in the global environment will have the name C1. So we construct a name here, C1, and say that equals that. Now, if I also make another counter, C2 to be make counter say starting with 10, then I do essentially the same thing. I apply the make counter procedure, which I got from here, to make another frame with n being 10. Okay, that frame has the global environment as its parent. I then construct a procedure which has that as its frame of definition, which is the code of it is the procedure of no arguments, which does something, which does a set, and so on, and n comes out. Okay, and C2 is this. Well, you're already beginning to see something fairly interesting. There are two n's here. There's not one n. Each time I called make counter, I made another instance of n. These are distinct and separate from each other. Now let's do some execution, use those counters. I'm going to use those counters. Well, what happens if I say C1 at this point? Well, I go over here and I say, oh yes, C1 is a procedure. I'm going to call this procedure on no arguments, but it has no parameters. That's right. What's its body? We'll have to look over here because I didn't write it down. It said, set n to 1 plus n and return n. Okay, increment n. Well, the n it sees is this one. So I increment that n. That becomes 1. And I return the value 1. Okay? Supposing I then call C2. Well, what do? I see C2 is this procedure which does the same thing, but here's the n. It becomes 11. And so I have an 11, which is the value. I then can say, let's try C1 again. C1 is this. That's 2. So the answer is 2. And C2 gives me a 12 by the same method, by walking down here, looking at that, and saying, here's the n I'm incrementing. So what I have are computational objects. There are 2 counters, each with its own independent local state. Now let's talk about this a little. This is a strange thing. What's an object? It's not at all obvious what an object is. We like to think about objects because it's economical to think that way. It's in an intellectual economy. I am an object. You are an object. We are not the same object. I can divide the world into 2 parts, me and you, and then there's other things as well, such that most of the things I might want to discuss about my workings do not involve you, and most of the things I want to discuss about your workings don't involve me. I have a blood pressure, a temperature, a respiration rate, a certain amount of sugar in my blood, and numerous, thousands of state variables, millions actually, or I don't know how many, huge numbers of state variables in the physical sense, which represent me, the state of me as a particle. Okay? And you have gazillions of them as well. And most of mine are uncoupled to most of yours. Okay? So we can compute the properties of me without worrying too much about the properties of you. If we had to work about both of us together, then the number of states that we'd have to consider is the product of the number of states you have and the number of states I have. But this way, it's almost the sum. Now, indeed, there are forces that couple us. I'm talking to you and your state changes. I'm looking at you and my state changes. Some of my state variables, a very few of them, therefore, are coupled to yours. If you were to suddenly yell very loud, my blood pressure would go up. Okay? However, and it may not be always appropriate to think about the world as being made out of independent states and independent particles. Lots of the bugs that occur in things like quantum mechanics, or the bugs in our minds that occur when we think about things like quantum mechanics, are due to the fact that we're trying to think about things being broken up into independent pieces, when in fact there's more coupling than we see on the surface, or that we want to believe in, because we want to compute efficiently and effectively. We've been trained to think that way. Well, let's see. How would we know if we had objects at all? How can we tell if we have objects? Consider some possible optical illusions. This could be done. Okay? These pieces of chalk are not appropriately identical, but supposing you couldn't tell the difference of them by looking at them. Right? Well, there's a possibility that this is all a game I'm playing with mirrors. It's really the same piece of chalk, but you're seeing 2 of them. How would you know if you're seeing 1 or 2? Well, it's but there's only one way I know. You grab one of them and change it and see if the other one changed. And it didn't. So there's two of them. Okay? On the other hand, there's some other screwy properties of things like that. Like, how would we know if something changed? Well, we have to look at it before and after the change. The change is an assignment. It's this moment in time. But that means we have to know it was the same one that we're looking at. So some very strange and unusual and obscure and I don't understand problems associated with assignment and change and objects. I mean, these things get very, very bad. For example, here I am a particular person, particular object. Okay? Now I can take out my knife, okay, and cut my fingernail, right? And a piece of my fingernail has fallen off onto the table. I believe I am the same person I was a second ago, but I'm not physically the same in the slightest. Okay? I have changed. Why am I the same? What is the identity of me? Well, I don't know. Okay? Except for the fact that I have some sort of identity. And so I think by introducing assignment and objects, we have opened ourselves up to all of the horrible questions of philosophy that have been plaguing philosophers for some thousands of years about this sort of thing. It's why mathematics is a lot cleaner. Let's look at the best things I know to say about actions and identity. We say that an action A had an effect on an object X, or equivalently, that X was changed by A if some property P which was true of X before A became false of X after A. That's a test. But it still means I have to have the X before and after. Or the other way of saying this is we say that two objects X and Y are the same if any action which has an effect on X has the same effect on Y. However, objects are very useful, as I said, for an intellectual economy. Right? One of the things that's incredibly useful about them is that the world is, we like to think about, made out of independent objects with independent local state. We like to think that way, although it isn't completely true. Okay? When we want to make very complicated programs that deal with such a world, if we want those programs to be understandable by us and also to be changeable, so that if we change the world, we change the program only a little bit, then we want there to be connections, isomorphism, between the objects in the world and the objects in our mental model. The modularity of the world can give us a modularity in our programming. So we invent things called object-oriented programming and things like that to provide us with that idea, to provide us with that power. But it's even easier. Let's play a little game. I want to play a little game showing you an even easier example of where modularity can be enhanced by using an assignment statement judiciously. One thing I want to enforce and impress on you is don't use assignment statements the way you use it in Fortran or BASIC or something, or Pascal, to do the things you don't have to do it with it. It's not the right way to think for most things. Sometimes it's essential, or maybe it's essential. We'll see more about that too. Okay, well, let me show you a fun game here. There was a mathematician by the name of Cesaro, or Cesaro, I suppose it is, who figured out a clever way of computing pi. It turns out that if I take two random numbers, two integers at random, and compute their greatest common divisor, their greatest common divisor is either 1 or it's not 1. If it's 1, then they have no common divisors. If their greatest common divisor is 1, well, the probability that two numbers chosen at random, has greatest common divisor 1 is related to pi. Okay? In fact, yes, it's very strange. Of course, there are other ways of computing pi, like dropping pins on flags and things like that. It's sort of the same kind of thing. So the probability that the GCD of number 1 and number 2, two random numbers chosen, is 6 over pi squared. I'm not going to try to prove that. It's actually not too hard. It's sort of fun. How would we estimate such a probability? Well, the way we do that way we estimate probabilities is by doing lots of experiments and then computing the ratios of the ones that come out one way to the total number of experiments we do. It's called Monte Carlo. And it's useful in other contexts for doing things like integrals where you have lots and lots of variables. You have space which has many dimensions you're doing an integral in. But going back to here, let's look at this slide. Okay. We can use Cesaro's method for estimating pi with n trials by taking the square root of 6 over a Monte Carlo experiment with n trials using Cesaro's experiment, where Cesaro's experiment is the test of whether the GCD of two random numbers, and you can see that I've already got some assignments in here just by what I wrote. The fact that this word rand in parentheses, therefore that procedure call, yields a different value than this one, at least, and that's what I'm assuming by writing this way, indicates that this is not a function, that there's internal state in it, which is changing. Okay? But it's the probability, sorry, the GCD, if the GCD of those two random numbers is equal to 1, that's the experiment. So here I have an experimental method for estimating the value of pi, where I can easily divide this problem into two parts. One is the specific Monte Carlo experiment of Cesaro, which you just saw, and the other is the general technique of doing Monte Carlo experiments. And that's what this is. If I want to do Monte Carlo experiments with n trials, a certain number of trials, and a particular experiment, the way I do that is I make a little iterative procedure which has variables the number of trials remaining and the number of trials that have been passed, that have gotten true. And if the number remaining is 0, then the answer is the number passed divided by the total number of trials, which is the estimate of the probability. And if it's not, if I have more trials to do, then let's do one. We do an experiment. We call the procedure, which is the experiment, on no arguments. We do the experiment. And then if that turned out to be true, we go around the loop, decrementing the number of experiments we have to do by 1, and incrementing the number that were passed. And if the experiment was false, we just go around the loop, decrementing the number of experiments remaining and keeping the number passed the same. We start this up, iterating over the total number of trials with 0 experiments passed. A very elegant little program. And I don't have to just do this with Cesaro's experiment. It could be lots of Monte Carlo experiments I might do. Of course, this depends upon the existence of some sort of random number generator. And random number generators generally look something like this. Okay? There is a random number generator is in fact a procedure which is going to do something just like the counter. It's going to update an x to the result of applying some function to x, where this function is some screwy kind of function that you might find out in Knuth's books on the details of programming. Knuth has these wonderful books that are full of the details of programming, because I can't remember how to make a random number generator, but I can look it up there and I can find out. And then eventually I return the value of x, which is the state variable internal to the random number generator. That state variable is initialized somehow and has a value. And this procedure is defined in the context where that variable is bound. So this is a hidden piece of local state that you see here, and this procedure is defined in that context. Now that's a very simple thing to do. That's very nice. Supposing I didn't want to use assignments. Supposing I wanted to write this program without assignments. What problems would I have? Well, let's see. I'd like to use the overhead machine here. Thank you. Here's well, first of all, let's look at the whole thing. It's a big story, right? Unfortunately, which tells you there's something wrong. Okay? It's at least that big. And it's monolithic. I mean, you don't have to understand or look at the text there right now to see that it's monolithic. There isn't a thing which is Cesaro's experiment. it's not pulled out from the Monte Carlo process. It's not separated. Let's look why. Remember, the constraint here is that every procedure return the same value for the same arguments. Every procedure represents a function. Okay? That's a different kind of constraint, is when I have assignments, I can change some internal state variable. So let's see how that causes things to go wrong. Well, let's start at the beginning. The estimate of pi, it looks sort of the same. Okay, what I'm doing is I take the square root of 6 over the random GCD test applied to n, whereas that's what this is. But here we're beginning to see something funny. The random GCD test of a certain number of trials is just like we had before, an iteration on the number of trials remaining, the number of trials that have been passed, okay, and another variable x. What's that x? That x is the state of the random number generator. Okay? And it is now going to be used here. The same random update function that I have over here is the one I would have used in the random number generator if I were building it the other way, the one I get out of Knuth's books. Okay? X is going to get transformed into x1. I need 2 random numbers. And x1 is going to get transformed into x2. I have 2 random numbers. I then have to do exactly what I did before. I take the GCD of x1 and x2. If that's 1, then I go around the loop with x2 being the next value of x. You see what's happened here is that the state of the random number generator is no longer confined to the insides of the random number generator. It has leaked out. It has leaked out into my procedure that does the Monte Carlo experiment. But what's worse than that is it's also, because it was contained inside my experiment itself, Cesaro, it leaked out of that too, because Cesaro called twice has to have a different value each time if I'm having a legitimate experimental test. So Cesaro can't be a function either. Okay? Unless I pass it the seed of the random number generator that's going to go wandering around. So unfortunately, the seed of the random number generator has leaked out into Cesaro from the random number generator. That's leaked into the Monte Carlo experiment. And unfortunately, my Monte Carlo experiment here is no longer general. The Monte Carlo experiment here knows how many random numbers I need to do the experiment. That's sort of horrible. I've lost an ability to decompose a problem into pieces because I wasn't willing to accept the little loop of information, the feedback process that happens inside the random number generator before, that was made by having an assignment to a state variable that was confined to the random number generator. So the fact that the random number generator is an object with an internal state variable, it's affected by nothing, but it'll give you something, and it applies force to you. Okay? That was what we're missing now. Okay. Well, I think we've seen enough reason for doing this, and it all sort of looks very wonderful. Wouldn't it be nice if assignment was a good thing? Maybe it's worth it, but I'm not sure. As Mr. Gilbert and Sullivan said, things are seldom what they seem. Skim milk masquerades as cream. Are there any questions? Are there any philosophers here? Anybody want to argue about objects? You're just floored, right? And you haven't done your homework yet. You haven't come up with a good question. Oh, well. Hey. Oh, sure. Thank you. Let's take the long break now.